Okay, I think we can start. Yeah. So good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione, and I have the pleasure of introducing to you today's speaker, Professor Matthias Troja. Matthias studied at the ETH in Zurich, and after some postdoctoral activity in Japan, he was appointed professor of computational, I don't remember, computational science or computational physics at the ETH in Zurich, where he's been until 2017, when he accepted an offer from Microsoft. And since then, he's in charge of the development of applications for quantum computing at Microsoft in Seattle. Yeah? Matthias is also a professor at the University of Washington at the moment. He's a fellow of the American Physical Society, vice president of the Aspen Center for Physics. He won the prestigious Raman Prize for Computational Physics of the American Physical Society and many other important prizes for theoretical physics and computational science. Yeah. So Matthias, we are really very happy that you accepted your invitation, and we are all very keen to listen to your talk. Yeah. And if you would like to start sharing your screen now, you're welcome to start with your presentation. And while your screen comes up, I just remind the participants to ask their questions using the question and answer facility, and Dr. Sinaisky, who you see in the panel, will moderate the question session after the presentation of Professor Troja. So Matthias, thank you very much again, and we are looking forward to your presentation.
Okay, thank you, Francesco. It's always great to see you and talk to you and your colleagues. And my last trip, basically, before the COVID crisis, was to the summer school in South Africa, and so that remains the strong memory for me. Now, quantum computing. The big thing is here that always new physics in the past has led to new technologies. For example, the invention of thermodynamics led to the steam engine and the Industrial Revolution. The invention of electromagnetism led to electronics, computing, and really changed what we do. And now quantum computing is starting now, but quantum already can be seen to start the next revolution. Because if we think back, it starts a really new form of computing, because deep down the abacus works on the same principles as the latest the classical CPU, but quantum computing is different. To see how, let's look at light. The light is a wave. The wavelength determines the color, but light is also a particle, namely the photon. Similarly, the electrons are particles that fly around the nucleus. But then the question by de Broglie was kind of, if a photon is a wave and a particle, and an electron is a particle, can it also be a wave? He proposed that in 1924, and within 5 years of his PhD, he got the Nobel Prize once it was confirmed that electrons are the waves as well. And now we view them as the waves around the nucleus, namely the chemical orbitals. Now you can ask the same about the classical bit to store data. Let's assume we have two boxes and one electron. If the electron is in the left box, the bit is 0. If the electron is in the right box, the bit is 1. But that assumes that the electron is a particle. What if the electron is a wave, and it's a wave that is in both boxes? There's a quantum bit, a bit that can be 0 and 1. That's in a wave state of the left and the right box here. Now, when you have that, describing the system classically gets hard. Because when I have one quantum bit here, the electron can be in the left box and in the right box. I have an amplitude for the wave in the left box and the right box. Now, what if I have two quantum bits? When I have two qubits, when I have two boxes, then there are 4 amplitudes. When I have 3 qubits, there will be 8 amplitudes, 0, 0, 0, 0, 0, 1, and so on, all the way to 1, 1, 1. Now that I can store easily. But what if I have 20 qubits? When I have 20 qubits, then I have 2 to the power 20 or 1 million configurations. I need 16 megabytes to store the waveform of that. Well, I can still do that on my smartphone. If I have 30 qubits, I need 16 gigabytes of memory. I may need my laptop to store the 1 billion amplitudes of the wave. Let's say I go to 50 qubits. Now I have 2 to the power 50 or 10 to the power 15 amplitudes that needs 16 petabytes of memory. And we're just starting to build classical machines with that much memory. What about 60 qubits? 60 boxes, it's 2 to the 60, and it gets hard. But let's say we go to 250 quantum bits, 250 of these boxes with 250 electrons. Then there are more configurations than there are negative atoms in the universe. So we will never build a classical computer to store that kind of state. But that just means it is hard to describe a quantum system like 250 qubits. We want to use it to build a computer. And when I was on a panel with Paul Messina, who's the director of the science from the Argonne Labs, we talked about enabling technologies for beyond the exascale computing. So what do we need to do to make machines that are more than 1,000 times faster than what we can do today? But he said, look, we're not just looking at something that is just 1,000 times faster. We're looking for something that will result in the phase change to truly new paradigms of computing. So doing things that we just could not imagine doing. And quantum computing will be able to do that. Let me show you one example. Here's the so-called the RSA 2048 challenge. This is a number with 2048 bits. And it is the product of 2 prime numbers. And the question is, can you determine the two prime numbers that when you multiply them, give this number here? And that is hard classically, and because it's hard, it forms the basis of the widely used the RSA encryption schemes. So classically, calculating that would take about 1 billion years. That's a long time. So I'd say this is intractable because I cannot wait a billion years for it. But on a quantum computer, I could solve the same problem in just a day. So that shows that with quantum computers, in this case, I need roughly 6,000 quantum bits, good ones. I can solve a problem in a day that classically might take 1 billion years. Now that specific problem is not so interesting because I don't want to break encryption. And once I have the quantum computer to do that, we'll have changed our encryption schemes to something that is not vulnerable to the quantum computers. So the question that I ask a lot every day is, what are other things that we will be able to do once we have a quantum computer? And when I first started asking that 7 years ago, 8 years ago, people asked, why do you ask the question? And the answer is simply, we need to do that because it will cost money to build one. It will take lots of time and lots of money, and so we have to know why we do it. And then people started thinking, and they heard things like, we will use it for better drugs, we will use it to counter climate change, to cure cancer, to fight hunger, fold proteins, and so on. So there were lots of things that people mentioned that we will do with the quantum computer. And then when I asked, how will we, let's say, use a quantum computer to cure cancer, the answers got very vague. And so it became clear very quickly that this is a list for a quantum wishing well. This is a list of hard computational problems where we want to have a way of solving them better and faster. But it was not clear yet how quantum computers can help with it. It is clear that those are really interesting problems, but we now need to start thinking about how could quantum computers help for some of them to really make progress. And that's what my team does. So we develop quantum applications. And for that, first you need to find a quantum algorithm with quantum speedup. Then after you've done that, you need to confirm that the quantum speedup remains once you not only look at the algorithm, but once you really implement all of the I/O for the problem, the input and the output. If there's still quantum speedup there, then I want to optimize the code to make sure the runtime is short enough. Because I want my calculation to finish in, let's say, a few months of runtime. I don't want to wait a billion years. And once that is done, once I think it can be fast enough, then I need to really map it to certain hardware and check once more that it works. So far, most of the research has been on the first step. Finding quantum algorithm and proving that asymptotically for large problem sizes, there's a quantum speedup. I mean that the time to solution scales better than a classical algorithm. That has been done by quantum information theorists. But what we need now more and more are quantum software engineers who look at the code, implement it, check it all, check the scaling, optimize the code, make it faster. That is a big task, and that's where we need to train more people to do that. So I want to walk you through these steps now for some examples. First of all, for quantum algorithms with quantum speedup, there's a nice list maintained by my colleague Stephen Jordan, who keeps the quantum algorithm zoo, which is a web page of all the known quantum algorithms and their speed up. But I mentioned that is not enough. We next need to look at I/O. And the typical example there is the database search problem, where the Grover's algorithm states that if you have an unsorted database, let's say a phone book, and I want to look up the name based on the phone number, then if I have a classical phone book, then I can't just look up the number, but I have to leaf through the phone book and I have to look at every single name to check whether the phone number matches. And so with n entries in there, n names, I need to look at n different numbers until I find it. But if I have a quantum computer with Grover search, I in principle need to look only the square root of n times. So there is a quadratic speedup, and that's quite often like here in a document from the European Quantum Flagship, database searches are mentioned as one of the applications for quantum computers. However, that ignores one fact, namely that also the quantum computer has to load the data. I have to get all of the phone numbers into the quantum computer for it to be able to find it. But as I load the data, I can already look for the number and find it. So that actually, once I look at the time it takes to load the data, then I realize, say, the time to load the data is the same quantumly and classically. And once I've loaded the data, I found the number. And it's worse, actually, because for the classical algorithm, I go once through the phone book from start to finish, and I'm done. The quantum algorithm looks into the phone book quantumly. So whenever it looks not just at one number, but it looks at all numbers. And so while I have to look only root n times, I have to look root n times at all n numbers, and so that actually the complexity is worse. So because the quantum computer has to load the data, whenever we have to load data, we have to carefully check whether that will not ruin my quantum speedup as it does for the searches in databases. So that's why I say that on a quantum computer, they're good for big compute problems and not big data problems. Often you hear that quantum computers will finally solve the big data challenge. That's not the case. I/O will be much slower, but when it's a problem that you describe by small data, but it's a big calculation, that's where they will be great. One example is factoring. A number with just 20 to 48 bits, it would classically take you 1 billion years. A second problem is quantum systems, quantum simulations. Small molecules like caffeine, I can solve easily, classically on a supercomputer. Big molecules, like MoCo with lots of the heavier metals in there. That's a challenge due to the quantum correlations, I will not be able to solve it accurately classically. It might take me again 1,000,000 years. So let's look at one example. I want to solve global warming. That was one of the bubbles of what we'll be able to do with quantum computers. And the way we could tackle that is by using quantum computers to look for a catalyst for carbon fixation. So can we find a catalyst that helps me remove carbon from the atmosphere by making it by making it react with hydrogen to turn into the water and the methanol, which would then be a nice fuel to use again. So what is needed to get there is we need to find a catalyst, and that takes lots of the trial and error. The question is, can we compute it? Can we predict how it works? And here's the one example that we looked at, the catalytic cycle that on the top left starts with this is CO2 molecule that reacts with the catalyst, goes through many steps, and out comes the methanol. Now, unfortunately, that catalyst, if it isn't effective, it is used up quickly, and so we need to find something better. But in order to do so, we need to simulate many such reactions and find out how it works. And in order to find out which direction it goes, which reactions happen, I have to calculate the energy differences between the initial molecules and the final ones, and then the reaction rate is given by Arrhenius' law. So it depends exponentially on the ratio of the barrier height EA and the temperature. And so in order to predict it, I have to very accurately calculate the energy difference. Second example, the nitrogen fixation. I want to take nitrogen from the air, to turn it into the ammonia to make the fertilizer. And that's a big challenge that needs a big industrial plant that takes lots of time. The energy, the methane, and so on to make. Now, nature can do it faster because we know that in the roots of certain plants there are microbes that can turn nitrogen from the air into the ammonia at room temperature, the ambient pressure, easily. And we don't know how because the molecule at the center of the protein here, the mocha, is just too complex to simulate classically. So what can we do? We realized that actually, while I can't do it classically, nature knows the properties of this, because nature uses quantum. Nature doesn't have to compute that the leaf is green. It just knows it because nature uses quantum mechanics to run. And so Feynman proposed too long ago that because nature is quantum, we should use a computer that uses quantum physics to simulate nature. And while classically, if I want to look at a molecule, to look at the occupation of the spin orbital, I need two numbers for one of them, I need 4 for 2 and so on, and I need x the potential memory for the n orbitals, simply because the wave function is exponentially large. But in a quantum computer, I need just 1 qubit per spin orbital. So with a few hundred quantum bits, I can solve problems that are classically intractable. And then I use it in a big calculation of my reactions. I use the quantum the computer on the right here to accurately calculate the energies. And with that, find out how such reactions work. So in principle, the quantum computer is efficient and is fast for doing that. And then we looked at the time it takes to solve such a problem. And we took the state of the art algorithm. We calculated the number of qubits it needs, that's a few hundred. We calculated the number of operations I would need to do it. I made the code nicely parallel, and I said, what if I have a quantum machine that can do a gate operation in 100 nanoseconds? Then I found out the runtime is much, much better than classically. It will not take 1 billion years. It will only take 300,000 years. Well, that's not good because we don't want to wait 300,000 years for one calculation to finish. So what one has to do next is one has to optimize the algorithm. We have to see, can we bring the runtime down? Because it will not wait for 300,000 years. And one thing is easy, I can make it parallel. I could just say, let us build a machine that has 300,000 times more qubits and run it massively parallel, and maybe we can bring it down to a year. But I also don't want to build a machine now with 3 billion qubits. And so we have to improve the algorithm. And we could do that. We could bring it down by tricks similar to that we use to optimize the classical calculations. We reused results instead of retributing them, which saved us a factor n, which here was roughly 100. We reordered the code pieces to make parallelization more efficient. That gave us a second factor n, or 100. We made the local the computation faster by a factor 4. We reordered the terms, which made the errors smaller and thus allowed us a bigger time step. That saved us a factor 10. We then said that while the big terms, the big forces, we need to do with the small time steps. The weak forces from electrons far apart could be done with bigger time steps. Using all of those tricks combined helped us bring the runtime down by a factor that was more than 1 million, and helped us bring down the runtime to about a couple of weeks. And that really shows how the quantum software engineering is essential to showing what problems we can do quantumly. Now, the bad news is that the assumption of a quantum computer doing a logical gate operation in 100 nanoseconds is optimistic, and we now think that it may be 100 times slower. Now, what if it's 100 times slower? Then it doesn't take 2 weeks. It takes 200 weeks or 4 years. But fortunately, in the meantime, we have even faster algorithms which bring the runtime down again, even if the gate times are slower. So that shows that we really need to build more and faster quantum software. And how do we do that? For that, we built the Microsoft the quantum development kit, which is a programming language of the Q#, the development tools, the compiler, debugger, the simulators for you to check it out, and the resource here is that made that will tell you the runtime needed to run the big computation on future quantum computer, and that can be downloaded open source from our webpage. So once we have a big quantum computer, then we see we can do chemistry. But what else can we do? The cryptography is one example, the optimization, the machine learning are the others. Let me talk a bit now about quantum optimization. The idea is I want to find the minimum of a function that could be I want to optimally schedule machines. It could be I want to find the best assignments of your airplanes to routes. It could be I want to find the fastest foot traffic. And I do that by exploring many configurations. And when I'm stuck in a local minimum, like on the left here, and I want to go to better local minima as the arrows indicate, then classically I have to climb over the barrier in between, which may be hard. But quantumly, I can tunnel through the barrier, which can be much faster. So with quantum, the tunneling in quantum optimization, I can go through a barrier more efficiently than classically and find a better configuration faster. And the good news is that looking at quantum optimizers, we realized we can actually simulate quantum tunneling efficiently. So we can dequantize that. We can simulate the same process as efficiently classically as the quantum hardware can do. And that gives the rise to dequantized quantum-inspired algorithms that in the future can be even further accelerated by the quantum hardware. But the good news is that looking at how I would solve the problem on quantum hardware, I realized I can do quantum optimization on classical hardware. I made breakthrough classically, and we can use it today and don't have to wait for quantum hardware, and apply it to many problems in the circuit default diagnosis, this oil and gas discovery, materials, power grids, signal processing, and. I want to show you a few examples. One example is traffic. You all know being stuck in traffic, and the problem is when you optimize for traffic, then and every car uses the same app, then every car will take the same side road, and traffic jams will be worse. So what you have to do, you have to really globally optimize it. You have to say, let's not find the best route for one car. Let's find the best route for all cars on the road at once. And I want to show you in one example what that looks like. And we are using 5,000 vehicles. Each one should look at 10 different routes it could take. And as we optimize the traffic pattern here in Seattle, we find that the optimizer spreads out the cars more, so that then there is less traffic, faster routes, if we optimize 5,000 cars at once. The second example, I have a warehouse, I have trucks that should deliver the goods. And now I want to find out what is the best way of loading goods to certain trucks. We run the quantum optimizer and find something ultimately that reduces the route length by 37%, and I need 16% fewer trucks for the same task. A third example that we did was for magnetic the imaging, where we looked at the problem of optimizing the pulse sequences that you send in to make the images. And the group we worked with wanted to optimize it, but was told that is a problem that is far too hard to solve for any computer. So they came to us and asked, could a quantum computer help? we said, yes, it can, but we can already help you today with quantum-inspired optimization of classical hardware. And then we looked at their problems. We found an optimized pulse sequence that gave the plot on the left, which compared to the plot on the right looks basically the same for me. For the experts, it's a bit better, but more importantly, we can do it 3 times faster. And being able to do scans faster means it is easier for the patient. It is cheaper to do. One can do more. One wins a lot making that 3 times faster. And so there are many problems where quantum it can help cryptography, simulation, optimization, the machine learning, and more. And so our mission of the team is to solve the world's most complex challenges by developing the most scalable and impactful the quantum ecosystem. We want to solve problems that just seemed intractable before for using quantum. And you can start playing with it now already in Microsoft's the cloud in Azure. We built the open ecosystem that you can use to do things today. With access to quantum hardware from partners, the IonQ, the Honeywell QCI solutions from Microsoft and one qubit. Those are small systems to learn on, to build the scalable system that we need to do chemistry problems. We build a so-called topological qubit. We want to build a small qubit that is scalable so that we can build millions, but that is also robust, stable. And how do we make it robust? How do we make it insensitive to the errors? We basically encode information in the topological property like a knot in some quantum string. Because whether this rope here has a knot in it or not cannot be decided locally. When I look locally, I only see the rope. In order to find out whether the rope has a knot or not, I need to look globally. And local noise or local changes, when I move the rope locally, that changes the rope locally, but it will not change the fact whether there is a knot in the rope or not. And so using things like knots can be used to store data much more stably than using something local. And that's already what the Incas realized, who stored numbers in so-called equipus, which were not tied into ropes. So it's an old idea. We moved that idea to quantum. And that way hope to build a much better scalable quantum bit. The next challenge after doing that is the control. You may have seen the pictures of cryostats, stats of quantum computers with hundreds of cables going down for just tens of qubits. when you want to scale it to 1 million qubits, that might naively be 1 million, the device going down. So we worked on making your things scalable. And here's a chip, a small one, that needs just a few wires going in that can then control thousands of qubits. So there's lots to do. The hardware, the quantum bit, control, the software, and so on. My focus was on the software, on problems we could solve quantumly. I touched on the cryptography. I went deep into the chemistry simulations, how with quantum computers we can solve problems in chemistry that are intractable classically. Can use it for catalysis problems. Maybe find the catalyst for the carbon fixation. And then I mentioned optimization and how that has an impact already today. What I have not touched upon is machine learning for quantum, because that's still quite open. There's big potential in using quantum hardware there, but we don't really know yet how. So that's still research, and there can be big breakthroughs there that I look forward to. Thank you.
Yeah, thank you very much, Matthias, for a fascinating talk. And I'm sure we will have several questions that our participants would like to ask you. And I will ask now Ilya to please moderate the question and answer session. Ilya, please.
Okay, so we have a few questions, and I assume that the two first questions are related to the beginning of the talk. So when you were kind of talking about the numbers which are requiring for the storage, so the numbers mentioned for the storage are the same as you would get with classical bits. So that's when you were describing how many qubits you need to, or how many memory units you need to store the several number of bits. I assume that's what it's related to.
So I didn't fully get the question. Can you repeat it?
The numbers mentioned for the storage are the same as you would get with classical bits.
Yes. Okay, so the numbers I mentioned for storage. Yes, so in classical memory, let's say I have 10 bits, I would store a single 10-bit integer. I would store a single bit string of 10 bits in those 10 classical bits. So the state of a classical memory of 10 bits, I can represent with just 10 bits. But if I look at 10 quantum bits, then the quantum bits are not just in one specific configuration like 00011001110, but the quantum bits are in a superposition of 2 to the power of 10 states. So they are in the superposition of all possible values. So the memory I need to describe the state of the quantum bits classically is exponentially larger. Well,
Okay.
to store the state of 10 classical bits, I need 10 bits. To store the state of 10 quantum bits, I need 2 to the 10 of 1024 complex amplitudes.
Okay, thank you. And there is a kind of like follow up to the same question that also isn't the amount of necessary bits for Shor's algorithm is intractably large?
For Shor's algorithm, the number of classical bits or the number of quantum bits? Can you clarify that, please?
It's not specified, so we can assume that you can probably answer for both.
Yeah, so when you have a 2048-bit number and you want to find out the product of which integers gives you that, then you don't need much. You need 2048 bits to store the numbers, you multiply them, so you need a few thousand bits, and you can check it. So it's not the memory that's the problem, it's the time, because I need to really try out all possible prime factors. So the memory is not much, but the time is a problem. On the quantum computer, again, I need 2048 bits to store the number. I need to take two numbers, multiply it, check the output. So I need about 6,000 quantum bits. And 6,000 fault tolerant error corrected quantum bits. So 6,000 quantum bits is a large number, especially 6,000 good ones and not 6,000 noisy ones. So to do that with noisy qubits, I may need a few million of qubits. So a few million qubits is currently intractably large, but in 10 or 20 years, we can be there. But not now. I would not call it intractable, because classically on classical the chips, we now have billions of transistors. And so we can imagine scaling quantum computers to millions of quantum bits, but it's indeed a challenge.
Okay, thank you. The next question, is spatial simulation of reaction possible in near future using quantum computing?
Yes, people have shown it already, but so far only for problems that it could easily do classically. So if the question is, can I do it? The answer is yes. Can I do it better than classically? The answer is that will take a while. For those problems, we need millions of qubits. So it will be several years until we get there from the currently about 50 qubits to millions of good ones. That will take a few years.
Okay, thank you. So the next question is about the vehicle simulation. So the vehicle simulation shown, were they actually run on quantum hardware, or was it just a simulation of what quantum hardware could do one day?
Which simulations were there? I missed that.
The traffic simulations.
The traffic simulation, yes. So this was done using. So this was done in real time. You saw so that's the screencast of that code running real time on classical hardware. So there we can simulate the quantum tunneling with Monte Carlo methods on classical hardware. So that was an actual simulation done today on classical hardware using simulations of quantum hardware.
Okay, thank you. And the next question is related to the topological qubits, and that is traversing qubits using two riders with different speeds. Can one find the knot?
yes, so when you have a rope, for example, you need to look at the entire rope to find a knot. And the question is, if you go along it, so you can find a knot even if you go just with a single trace along the line and record where the rope goes. Then you can then look at it globally and find out if there was a knot. But you have to look globally. So we want something where it is possible to find out if there's a knot there or not, but where you cannot do it with just random local noise. So you can't just take a rope. Let me just take something here. So if I take my cable here, and I can make a knot in it by doing something global, but if I wiggle around locally, then the knot stays. So I have to really consciously do something big and global to undo the knot. So we want a system that does not react to local noise, local wiggling, but where I can consciously, with a global operation, look at the state or change it. And that's why kind of a knot in a string, or something topological, is perfect. And yes, the question said, if I go along the entire rope, yes, when I go along the rope, then I can always find the state. But when I wiggle locally, I cannot.
Okay, thank you. So there was also a question on the chat, which was related to the Monte Carlo and the quantum tunneling, but I think you also cover it while answering for the traffic question. And so there is a question again in the Q&A related to the D-wave. I don't know, can you answer that? So D-wave tunneling can be simulated classically using Monte Carlo simulations. Isn't it true?
Yes, that is true. On that machine, I can simulate. Now, what does it mean to simulate? I cannot faithfully simulate the exact dynamics of the system, but using the Monte Carlo simulations, I can do a simulation that is closely related, that solves the same problem and that scales in the same way. So if I use D-wave as an optimizer, then I can simulate the way it solves the optimization problem efficiently with Monte Carlo simulation.
Okay, thank you. So there is no more questions in Q&A.
Okay, then Ilya, thank you very much for moderating the questions. So if there are no further urgent questions from the participants, I think it's time then to thank Matthias very much for his very nice and enthusiastic talk about quantum computing and its immediate prospects, yeah, which makes it even more exciting. Yeah. So Matthias, thank you very much again for spending time today with us. I know that the day just started for you, whereas for us it's slowly coming to an end. So we wish you all the best, and I also would like to thank our faithful participants that follow us every Monday afternoon. So, Emilia, thank you for moderating the questions so nicely. Yeah. So, thank you very much, Matthias, again, and I'm sure we will stay in touch, and hopefully sooner rather than later you will be able to join us again for another summer school in South Africa. Thank you very much.
I look forward to that.
Yeah. No, we look forward to that too. Yeah. No, thank you very much. So all and all of you stay safe. Yeah. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.